All right, for all you first-year engineering students out there, we're going to treat this as a must-know case review. We're about to tackle a question that's so fundamental you might not have even thought to ask it. Why is our entire world powered the way it is? It's a great story, so let's get right into it.
So here's the big question, the core puzzle we're solving today. You've got direct current, DC, which is, well, it's simple, right? It just flows in one straight line. Easy. But then, the power coming out of your walls, the stuff that runs literally everything, is alternating current, or AC, and it's constantly reversing itself, back and forth, back and forth. So why on earth would engineers build our entire global power grid on something that seems so much more complicated? That's what we're here to figure out. Okay, to really get to the bottom of this, we've got to properly meet our two main players. It's like a title fight. In this corner, direct current, and in the other, alternating current. Let's break them down.
First up, we have direct current, or DC. The easiest way to think about DC is like water flowing through a hose in one steady direction. It never turns back. It's that consistent one-way push of electricity. You see it everywhere in things like batteries, solar panels, the power bank for your phone. It's simple, it's predictable, it's, well, direct.
And then you have its rival, alternating current. AC is a totally different beast. Instead of a steady flow, AC is all about changing direction. The current flows one way, then, nope, it reverses and flows the other way. And it does this over and over in a perfect continuous cycle. Here in the US, that reversal happens 60 times every single second. This is the magic and the madness behind the power in every outlet in your house.
So when you put them side by side, you can really see how different they are. You've got DC, one direction, constant voltage, the stuff you get from batteries. Then you've got AC, constantly reversing, its voltage always changing, and it's what's supplied to pretty much every home and factory. And believe it or not, this one little difference, that back and forth motion, is the absolute key to understanding everything that comes next. Okay, so we've got the basics down. Now let's travel back in time a bit to the late 1800s. Engineers were facing this monumental problem, a real beast of a challenge. How do you actually build a power grid for an entire country?
And this was the million-dollar question, or, billion-dollar question, really. See, making electricity at a power plant is one thing, but how do you get that power hundreds of miles away to a city without losing most of it along the way? The problem is resistance. As electricity travels down a wire, a ton of it just turns into wasted heat. And with DC, well, trying to send it more than a mile or two was a disaster. So much power was lost. They absolutely had to find a better solution.
And the solution to this massive grid-killing problem, it turns out, it lies in one single knockout advantage that only AC has. This is the reason AC won the famous War of the Currents.
And here it is, the secret weapon. AC power can be easily stepped up to a super high voltage and then stepped down again. It's the ability to change its voltage on a whim. With DC, doing this is really, really hard and inefficient. But for AC, it's easy. And that one simple trick, that one capability, is what made our entire modern power grid possible. It's the whole ballgame, right here.
So what's the magical device that makes this possible? It's something you've probably seen a million times, the transformer. That simple box is the hero of our story. It's a remarkably clever piece of engineering that can take AC voltage and crank it way up or bring it way down. And here's the kicker, it only works with alternating current. The whole principle is based on the changing magnetic field that only AC produces.
So let's walk through the entire journey. It's actually a beautiful four-step process. First, you generate the power at the station. Then, step 2, and this is the critical part. A transformer steps up the voltage to incredibly high levels. We're talking hundreds of thousands of volts. Why? Because power transmitted at high voltage loses way less energy to heat. Then you transmit it across the country. And finally, right before it gets to your house, another transformer steps it down to a safe, usable level. This simple, elegant system is the backbone of literally every power grid on the planet.
So you can see why the choice was so clear, right? AC, with its ability to be transformed, solved the massive problem of long-distance transmission. It was efficient, it was economical, it just worked. DC, for all its simplicity, just couldn't compete on that front. It was game over.
But wait, this doesn't mean DC just vanished into thin air. Not at all. In fact, what happened was that this great war ended up creating two separate kingdoms, you could say. Two totally distinct domains where each current is king.
So AC totally reigns supreme in the world of big power. Think about it. The national grid, those massive motors in factories, all that heavy-duty equipment, and of course, the power flowing into your home. Anything that involves moving huge amounts of energy across huge distances, that's AC's turf.
But then, you've got the world where DC is the undisputed champion, the world of electronics. Everything from your smartphone and laptop to the tiniest little circuit board runs on DC. Computer chips just can't handle a current that's always flip-flopping. They need that steady, predictable flow. And of course, anything that runs on a battery, from your TV remote to a Tesla, is fundamentally a DC device.
So the real takeaway here isn't that one is better than the other. That's the wrong way to look at it. It's about having the right tool for the job. You need to send power 500 miles? AC is your champion, no question. You need to power a sensitive microchip or store energy in a battery? That's a job for DC, the master of electronics. They're just two different solutions for two totally different engineering puzzles. And this brings us to a really interesting final thought, one that looks to the future. The whole reason our world runs on AC is because of that old transmission problem. But think about what's happening now. We have solar panels generating DC. We have massive battery farms storing DC. These DC native technologies are becoming a huge deal. So, could the old rules be changing? Are we about to witness a brand new chapter in the epic story of AC versus DC? Well, that's a question that your generation of engineers is going to answer.